A lot of juggling. All right, there we are. So picking up where we left off earlier this week, we are looking at atomic packing factor. So this is quickly reviewing the body-centered cubic, where we have, through simple trigonometric relations, we have side length A and A, in this case, A not being equivalent exactly to the diameter of the individual atom. So you have 8/8 of an atom in this unit cell, body-centered cubic, and we get our AA and A squared plus A squared equals 2A squared, square root of that being square root of 2A. So that's the length of the base of our triangle here. And the height is A, because again, this is a unit cell, A by A by A. Square root of 3A, same idea. Square root of 2A squared plus A squared. Square root of that is the square root of 3A. That's where we get our total diagonal length across the unit cell. So it's trying to understand what this is. So the length overall is the equivalent of 4 radiuses, because there are 2 complete units or 2 complete atoms in this unit. So when we do the calculation for the volume, this is the volume of the atom, volume of the unit cell, 4/3 pi r cubed, volume of a sphere, fairly straightforward. 2 of those divided by A cubed give us the atomic packing factor for body-centered cubic of 0.68, and this is how we derive that. So that would be a good example of something to put on a test, I would think. All right, face-centered cubic is also a very important structure type. This is a little bit more dense even still, and is part of why we just touched on this, part of why these are such good examples of conductors, electrical conductors specifically. So aluminum, copper, gold, lead, nickel, platinum, silver, these are examples. They have a coordination number of 12. So many, many, many more individual atoms that are associated. So instead of just having 2, you have 6 face atoms, so 6 atom faces, meaning a half atom times 6, and then the 1/8 of an atom, so 8 of those, 1 at each corner, give you a total of 4 atoms per unit cell. So this is the most densely packed true cubic arrangement. So 12 immediate adjacent touching atoms, and that's why the coordination number is 12. So all of these are shown just to give you a better idea. Same kind of concept here. You're looking at the, for this one, you have the square root of 2A over 4. So square root of 2A, meaning it's the same this way, that way, the other way. That's what they're trying to represent with this diagram. So A, square root of 2A. So it's always through like 2 complete atoms in terms of the distance. So 4 total atoms per unit cell, 4/3 pi r cubed, volume of the atoms divided by the volume of the unit cell. Okay, so when you do the calculation, you get an atomic packing factor of 0.74. So 74% of the space in this unit cell is actually occupied by the atom. So this is one of the most efficient packing arrangements that there is, and that happens to be why these are very, very good conductors. It's also why some of these materials can be very dense and very heavy, because these atoms are packed so tightly. So that's the thing that makes sense. So you would expect something like lead to have this kind of packing arrangement, because this is something that we would expect. We would expect it to have the most number of atoms per a given volume as possible. So that's where we were. So there's a stacking sequence, and we can look at 2D projections of this. So looking on from the side, you can see A sites, which are the atoms themselves. You can see B sites, which are in between a couple of atoms. And then you can see they have just sort of a little bit of space, and it's kind of a little hard to tell by this diagram, but they have just a little bit of space. Then there's the C sites, which are slightly different in volume than the B sites. Not by a lot, but just enough. So looking at the next slice, we see our B sites. That's where the next stack of atoms goes. So in the voids there. And then the C sites. So the C sites are taking up some of the void volumes of the B level. So it's 3 different layers that you're looking at sequentially, in order to give you this stack. And then we take a cube out of that, basically. And so that's what they're trying to represent here in order to give you some sort of practical sense. So if you think about trying to stack ping pong balls, you have to pack them into the interstices, those interstitial spaces, in order for them to be densely packed and not moving around. But around the edges, that means that you might still have some open spaces and things like that. So where you can only fit half a ping pong ball, and since you're not cutting them in half, you're not going to put one there. This is just representing the 3 different layers. So you have A, you have the B level, and then you have the C level. So this is what is meant by a face-centered cubic unit cell. Now we take a look at taking that kind of a step further and looking at what's called hexagonal close packing structures. So you start to sort of see how close FCC and HCP can kind of be. So these are also the same atomic packing factor. So the density is the same at 0.74. And the ratio of height to distance between the atoms is about 1.663. So the stacking height. So here we have about another example of like the 2D projections. We have a top layer, we have a middle layer, and we have a bottom layer. So in this case, the bottom layer is the same as the top layer. So instead of being yet a 3rd position, they're evenly staggered. So they have the same packing density there. Cadmium, magnesium, titanium, and zinc are examples of things that are naturally found with hexagonal close packing. So this should be something that's that'll make a little bit of sense. We're going to do some slightly different things with calculations for hexagonal close packing, and there's a couple examples that you guys do for labs. So I imagine you guys have already seen that probably this week in lab, if I were to guess, where you've done some calculations, or you started to look at lattice parameters. I don't remember exactly what the lab sequence is now with the revision, but this will help kind of catch you guys up on the concept side. So you've got in hexagonal close packing, they're showing off their viewer, because again, 3D viewers were kind of a big thing back in the day, so they're really proud of it. So Um, so you have an AB layer, you have an AC layer, then you have ABA and ABC. So in this case, it's looking at those in terms of slices diagonally. The theoretical density is represented by the mass of the atoms in the unit cell divided by the total volume in the unit cell. Any guesses as to why this is a theoretical number? We've used the term that's the key for this, but any guesses as to why this is a theoretical density instead of the true density of the actual material? Let's see if you guys have any guesses, because the concept is density is number of atoms per unit cell times the atomic weight divided by the volume of the unit cell, which for cubic will be A cubed, times Avogadro's number, so the number of atoms per mole. Any guesses as to why this is the theoretical density and not the quote true density of the material? The key word that we're looking for there is defects. So we'll learn a little bit more about that as we go along, but defects are what's responsible for that. So the theoretical density in an idealized case for something like body-centered cubic, if A is 52 grams per mole for chromium, and we have a radius for that particular atom of 0.125 nanometers, and we have 2 atoms per unit cell because it's body-centered cubic, we can apply that and we get a density, a theoretical density of 7.18 grams per cubic centimeter versus the actual density of the material, which is 7.19 grams per cubic centimeter. So we know from experience that this is the way that it should be stacked, but in reality we will have defects in materials, and crystals are not all perfectly perfect all the time, as it turns out. So there's some other factors that can contribute to that, but we'll learn some more about those as we go along. So broadly speaking, metals are more dense than ceramics, which are more dense than polymers. So broadly speaking, you will have metals, especially some of the more noble types of metal, the more rare earth metals and things, they are more dense typically than some other things. This is why water-based density separation, gravimetric separation mechanisms are used in order to harvest those in small quantities. So there's also graphite and ceramics and semiconductors that are a little bit less dense, broadly speaking. So aluminum, magnesium are examples of low density metals. Alloys also fall in that same range, but they vary in between the pure substances. Then there are some of the polymers. So those tend to be even less dense still, broadly speaking. Then you have composites, and that's where their densities are going to be similar to something like magnesium or aluminum, depending on what variation it is. There's a range because there's a difference in how they are grown, and then toward the bottom typically are things like woods, which are the less dense of the fibrous materials actually. So That's why you can carry around a log, but if you were to try and carry around a gold bar of the same size, it's an order of magnitude heavier, or a couple orders of magnitude heavier. And so not everybody, as it turns out, can carry around several 100 pounds of material the same way. So things to keep in mind. The A lot of this is based on the fact that these fibers, especially for the composites, can be arranged differently. They can have different thicknesses of the epoxy matrix. The epoxies that are used can have different thicknesses. They have a different weight once cured because a lot of that solvent has evaporated off. There's lots of different factors that are incorporated. So this is just to give you kind of a sense of order of magnitude rather than an exact number density. So there's a lot of factors there. The metals have very close packing arrangements. So we've talked about that. Very often they're going to be BCC or FCC, so body-centered cubic or face-centered cubic typically. So they often have large atomic masses as well. The ceramics are going to be a little less dense. They often have lighter elements. And remember that a lot of their structure is based on the exchange of electrons rather than covalent bonding. So we've talked about some of the chemistry behind why those can be less dense. So they're often lighter elements than the metals, which have much higher atomic masses. The polymers have low packing density, and that's one of the biggest reasons why. So the polymers are not sort of hard atomic spheres in the same way, so they have much more free space, very low packing density, very low packing efficiency, and they tend to be mostly lighter elements, carbon, hydrogen, oxygen being kind of the three most common components. Sometimes there's some nitrogen and some other elements in there, but mostly lighter elements. So when a metal material starts out with multiple times the mass, multiple times the atomic mass there, that creates all sorts of headaches. Composites, there are intermediate values. They are also made of lighter elements, but then the epoxies add a lot of density to the material. So it is a hybrid of sorts between sort of the polymers and some semiconductor and ceramic-like materials because of the way that they are made. So the way that the composites are made, the way that the fabric layups are done, types and amounts of resins used, whether or not it's cured in an autoclave, whether or not it's vacuum bagged, and all of the sorts of things. All of that makes quite a big difference. So the building blocks of a lot of these materials that we're using, or the materials that we're focusing on this semester, are turbine blades and all sorts of very highly specific applications. But all of these are, even for commercial abrasives and things of that nature, all of these are crystalline materials mostly that we'll be focusing on. So we don't really think of metals as being crystalline materials, but there's some really, really good examples of some of these crystalline materials and how they function. So quartz is an example of something that fractures more easily than some other things because it fractures along crystal planes. And this is one of the first places that we can think of that we've actually experienced seeing crystallographic planes in action. So these are often structures that are very smooth on a few sides. They can often be optically near perfect and near transparent. Not always, but sometimes. And these are helpful. So polycrystalline materials rather than monocrystalline materials are different. So this is a highly colorized figure, but it's there to try and differentiate some of the individual grains. Most engineered materials are going to be polycrystals. So when are you going to see materials like this? This is an example of something that could be any one of a few different things. In this particular case, I happen to recognize this kind of grain structure as an electron beam weld. Yeah, that's what this one is. So it's an electron beam weld, highly controlled heat, but it still has a different grain structure in the center than it does at the edges, where it is isotropic. So the bulk material far away from the weld is isotropic, meaning similar size grains, even of different types of material. We'll talk about what that means soon when we get into phase diagrams and things. Just understand that each of these grains might have a slightly different ratio of elements in them compared to the one next to it. So maybe one of them has some carbon and the other one, the next door grain, does not, or something like that. So in this case, this is what is that? Niobium, hafnium, tungsten, I think is what this particular one is. So they weld these materials together using the electron beam, and each of those grains is an individual crystal. When the grains are randomly oriented, especially when they're of varied size, like they are in the center there, they are different. They're different for kind of a few ranges there. Okay. So each of these grains is considered a single crystal, even the larger ones, if they are of the same color. Grains aren't actually this color in real life, so we don't live in some sort of upside down clown world, except when people turn your building into a drive-through, and then we are living in an upside down clown town world, but that's a different story. So the grains randomly oriented are comprised of isotropic that are the same size, and these anisotropic, meaning not the same size. They are in different orientations. They are randomized. This is also something that demonstrates something that you guys will learn later in the semester with the weld lab. You will learn about the heat affected zone, or kind of get to see it in person. The heat affected zone where the E-beam, the electron beam, would have passed along the center, and you can see it sort of pulling the grains along, almost like the flow of a river as that element was heated. And the zones around that central line, so the E-beam, I'll try and see if I can clarify this a little bit with, again, some of the greatest examples that you've ever seen. I'll do red in the hopes that you can see it. So the E-beam would have been run down the channel like this. These regions that I'll outline with the green, this is the melt zone. In between the green here is the melt zone next to the E-beam, which is in the center. And then adjacent to that is what we would term the heat affected zone. So everywhere inside between the green and the blue here would be affected. It's actually a little bit more like this. So everywhere in here is affected. The actual crystals themselves are affected within this zone. I guess it kind of tapers off a little bit more there. But everything in that zone is in fact affected by the heat. So this material, because of being anisotropic and because of being larger grains, is in fact weaker than the adjacent isotropic grains of material. So this is a thing that will make it easier for you to understand why welds typically tear in this zone or this zone when a material is stressed after it's been welded. Typically, it's at the very, very, very edge of where the weld happened that welded material will sort of tear away from the other structure. And that's because you can see this very fine delineation between the fine grains of the strong material and these large grains of what is a considerably weaker material adjacent to it. So this is specifically true in vibration intense regions. So something like gold mining equipment in the Alaskan wilderness in extremes of temperatures. These zones here and here are exactly where you're going to see failure. So people are going to have to re-weld and re-weld and re-weld and re-weld the same spots. And they're just going to keep pushing this heat affected zone farther and farther and farther into the material until just the whole thing becomes one giant mass of weld. This is why that happens. There's some other factors like cyclic temperature and stresses and things that happen. So there are a few additional mechanisms at play, but it'll give you at least an idea of why it is that happens. So because those grains and the properties are not directionally oriented exactly, they don't have a strong or a weak axis really. So that's going to be sort of strong in compression, sort of, but very weak in tension. And that's typically where it fails, is vibration and tension that tends to pull those heat affected zones away from the stronger isotropic crystals. So commonly these grains are going to range from something like 1 nanometer to after that problem. So it's after that kind of processing that's happened to the material, 1 nanometer all the way up to about a couple centimeters for the grain size. So there can be just a handful or millions of atomic layers for the grains, and it can be sort of anywhere in between. So there's a lot that goes a lot more depth there that we could go into, but we'll keep rolling. So the single crystals versus polycrystals becomes important for a few reasons. The properties vary greatly with direction in anisotropic materials. So they might be really highly resistant to compression or tension in one direction versus another. The modulus, and it's sort of something that you can see why. If you tried to compress and push these grains against each other, so if you were in compression in this axis, grains are already fairly slim, so you're not going to be able to compress them very easily. So it's going to be pretty resistant to compression. If, however, you were to reverse it, and you were to try pulling it apart, same sort of thing, like in this direction. So if we go red, if we were to try and pull it apart, and we were pulling it in this direction as well, So we're trying to pull it apart. These grains have already been stretched out, so there's not a lot more instance where it's going to be it's not going to be as easy to pull it apart because these grains are already running in that direction. They've already been stressed in that direction. And we'll learn a little bit more about why this happens when we get to stress strain diagrams. But this is going to be farther in the stress strain diagram along this axis because of how these grains have already been stressed. Whereas out here, this material, if you try and compress it or pull it apart in tension, it's very hard for these grains to transfer material itself. But if you change directions and you start to try and pull away right here at the edges, that difference in size of grains is going to create a weakness in these materials. And so it's going to yield much more easily in that direction. And that's why that mechanism happens the way that it does. So hopefully that clarifies at least a little bit of what we're talking about there. So the modulus of elasticity for body-centered cubic and iron is what's shown here. So on the diagonal, because of where the grain boundaries are, because of where because of how those bonds work between the atoms, along the diagonal, the multiple grains, if you're trying to pull it, you have a diagonal modulus of elasticity of 273 gigapascals. But along the edge, so going in a different direction, this would be almost trying to shear planes of atoms off of each other. It's about half that, 125 gigapascals. So it's a little less than half, but in that range. So same material, pulled a different direction in a different kind of process or put under a different kind of stress, now is half the strength of what it would be in the correct orientation. So the grain structure and orientation relative to whatever your design application is matters tremendously. So I'm going to say that again and try and say it slowly enough that you grasp it. The grain size and orientation relative to the design load and end application is critically important in materials. The reason being, how that load gets transferred, how that shock, the weight that gets carried, the impact or impulse, whatever the design application is, the way that the material is stressed in its application, the directionality matters tremendously and can mean the difference between, literally can mean the difference between people being harmed when something fails and a bridge collapsing gracefully so that the material doesn't just disintegrate and fall, plunging everybody slowly to their death, but gives them, it bends and yields and absorbs the energy. Same kind of thing happens in car crashes and things like that. The parts of the car are designed in such a way so as to collapse over the course of a distance in order to absorb an energy. And so there's lots of chaos that happens as a result of that. So what we've got with these polycrystalline materials is because they have different grain sizes and orientations, their properties may or may not vary with the direction. It depends on how widely varied their sizes are, as well as the orientations. but the orientations being isotropic. If the grains are randomly oriented, but they are isotropic, the poly example here, the polycrystalline iron is on the order of about 210 gigapascals. So it's kind of an average between the two, with the edge and the diagonal. It's somewhere in the middle, but it's a little closer to the maximum strength along that edge. So the same material can give you widely differing results based on how it was processed, and we'll learn later on what its base composition looks like. So if the grains are textured, they are probably going to be anisotropic. And so there's all sorts of things that are happening in 3 dimensions, but a lot of the imagery that we're going to see is going to be 2-dimensional representations of those. So again, something to kind of keep in mind. Before we start talking about polymorphism, again, quick check for any questions. Today is going to be particularly concept heavy. So I'm going to try and get you guys all the way through this particular chapter. I'll keep an eye out to see if any come up. But when there's 2 or more distinct crystals for the same material, we've got what's called an allotropy, or commonly called a polymorphism. So there are multiple examples of this. A good one is something like titanium, which has an alpha and a beta orientation of the crystal structures. So there can be a couple at the same time. Carbon does this, for instance, so diamond and graphite. Chemically, they're identical. Crystallographically, they are very different. Graphite is in sheets and planes. Graphene is very much the same way. It's typically in sheets. Graphene has a little different orientation even still than graphite does, and different than diamond. Diamond is a 3-dimensional specific crystallographic form. Even though graphite can have exactly the same chemical composition and no impurities, it is not anywhere near the same kind of properties as diamond. So these are examples of different kinds of crystals using the same material, even if it's the same chemical formula. And this is why the crystallography behind metals are so important. So for iron, and this is one we're going to study the iron phase diagram to an extent where you'll literally see the phase diagram and you will actually have a vomit response, very likely. So don't worry, we'll get there. But for now, just understand that somewhere on the order of 900 C, you're still in base-centered cubic or body-centered cubic. Then as you go up in temperature, you start to see some gamma crystalline structures form until about 1394 C. And then you'll see face-centered cubic form. So the gamma form, then sigma goes back to body-centered cubic again, but at this higher temperature. So again, think of all of that thermal energy, think of all of those valence shells and the electrons having more and more energy, and those atoms physically starting to sort of swell in size, just like a balloon. If you heat it up, that gas inside has to expand to accommodate all of that extra kinetic energy. Well, the electrons are whizzing around faster and faster and faster and faster, so their orbit expands, so they step up in energy levels in order to store all of that kinetic energy of that higher level of temperature. And then above 1538, that same given composition becomes liquid. And so then you have a liquid iron above, typically somewhere in the range of like 1600 or so C, which is really stinking hot. Really, 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 really high temperatures. So you have multiple different types of crystalline structures. And even though it alternates back and forth between body-centered and face-centered cubic, you're having physical changes in the crystals that happen until it becomes a liquid. And so then it's completely amorphous and it is no longer the same. So a unit cell within these crystal systems tend to have, we're looking at the unit cell being a smallest repetitive volume that contains all of the lattice pattern information about a crystal. So A, B, and C are the lattice constraints. So what this does is this tells us what constraints the lattice has to abide by in order to fully contain the pattern of that lattice. So there are 7 different crystal systems and there are 14 different lattices in total. This is just trying to give an example. Yeah, awesome. Yet more things. Okay. Okay. Yet more problems to solve. Great. So there are point coordinates that we're going to be showing how to do some calculations on. There's 111 is a very common point coordinate system for certain crystal types. You have experienced 111 crystalline fractures in your time because they tend to, when they fracture, they tend to form very sharp shards, and they tend to be often at the smallest sizes, they tend to be exceedingly sharp. So if you've seen something like simple float plane glass, simple soda lime glass fracture, you have seen probably an example of something like 111 crystallographic plane fracture. The 111 is the coordinates X, Y, Z, one for each of them. So 000 being the origin. This means that the unit cell corner are positioned at 111. And the point coordinates for any given unit cell are half A, half B, half C. So there's going to be integer multiples of the lattice corners that are going to help us understand what the position is within that linear cell. It'll make sense in the context of some examples. So there's an algorithm that's used to determine this. The coordinates of the vector to tail, the coordinates of the vector tail, we'll look at kind of a few examples of these. So you have x1, y1, and z1, and then you have the vector head is going to be at x2, y2, z2. So that looks like this. So you have the tail is at 0, 0, 0. Y1 is 0, Z1 is 0. You have the head. So this is X2, Y2, Z2. So X is at A, but y is at 0, and z is at half c. So we want to normalize the coordinates. We're going to subtract the difference between, we're going to subtract x2 minus x1, y2 minus y1, z2 minus z1, and divide by the size of A, B, and C, whatever our distances are for that cell, then adjust to the smaller values of those. So we'll try and drop this out of the way a little bit. So A minus 0, 0 minus 0, half of C minus 0 divided by A, B, and C. So again, you guys are going to do, I think, some exercises in lab that are going to make use of these same calculations. So these are going to be pretty important to understand. Then we're going to basically adjust to the smallest integer values. So it's going to be, instead of 1, 0, half, we're going to multiply all of those values by 2 to get rid of the denominators so that we have whole integers to work with. So that's a step that a lot of people forget is right here. We go from 1, 0, half up to 2, 0, 1. So it's the same numbers, just scaled up. It's the same directionality. So then we enclose in square brackets with no commas. This is the crystallographic directions. So this is representing 201 is the direction of the crystal. So we're going to look at, there can be a number of different orientations of these. This is just showing you a vector that's going through the atoms to show you what directions they're at. So the crystallographic directions. Here's another example that we'll walk through. So the tail starts here. So this would be X is at A, Y is at half of B. So Y is halfway, it's at the midpoint. Z is at 0 because it starts on the XY plane and goes up to C. So it goes all the way up to the full height of Z. We always represent that as A, B, and C just to keep things simple. So X2 is minus A because it's going in the opposite direction. So it's going onto the negative side. Y2 is B because it's again on the positive side and it's all the way up into that corner. Z2 is C. So minus A over A, B minus B over 2 divided by B, C minus 0 divided by C. So minus 2, 1 half, and 1. So then we normalize, meaning we multiply through by the denominator to get the fraction, get rid of the fraction. So minus 4, 1, and 2 are crystallographic directions for this particular example. And whenever we have a negative, we put a bar over the top in order to indicate that, just so that it's clear and it's not a mistaken mark. It was something that they started doing as a good discipline in lab notebooks when they were starting to take a look. So there are also families of directions, and they have a visualizer to help you see, again, just some additional examples of these things. The linear density is different from the atomic packing factor, and the linear density is determined based on the number of atoms divided by the unit length of a direction vector. So on a 110 or a 110 direction vector for, in this case, face-centered cubic, what we look at is for something like aluminum in the 110 direction, we have um, an A value that is about 40 or 0.405 nanometers. So we have two atoms that crosses. So it's the distance across two atoms divided by the length. So root 2a, again, coming from the trigonometric value a, and or in this case, a, and the square root of a. And what we get is about 3.5 inverse nanometers. That is a kind of an important number, but we're not really going to spend a lot of time dwelling on why. It's just an idea. It's 3.5 atoms per nanometer is what it's telling you. So inverse nanometers meaning per nanometer, 3.5 aluminum atoms per nanometer. So that's what the linear density is representing. When we go to do hexagonal close packing, the directions change a little bit because we're using triangular coordinates instead. And that causes some question for concern. So, all right, things that we want to take a look at are we want to understand what the process is in order to determine these coordinates. So we start by moving the brackets. In this case, we have a 1, 2, and 3. And each of these axes is different. So we need to keep in mind kind of how this is moving. So we're going to remove the brackets. We're going to divide by the largest integer. So all the values are less than 1, so that we have fractions. And then we're going to multiply the terms based on what the appropriate unit cell dimensions are. A1, A2, and A3, or C as the total height or Z, in order to produce the projections for these. So putting together the vector places a tail at the origin and then stepping off of those projection steps in order to figure out where the head goes for the parameter. So if we were tasked to draw 1 bar, 2 bar, 1, 3 direction vector in a hexagonal unit cell, while that sounds like some sort of Germanic torture, it's actually not quite as scary as it sounds. So let's take a look at it. So we start out with A1, A2, A3, and Z coordinates, and we want to remove the brackets as step 1. So we have -1, -2, 1, and 3. Okay, so that's not so scary. Divide by 3, because that's our largest integer. -1/3, -2/3, 1/3, and 1. Then our projections are going to be A times 1/3 minus the -1/3, -2/3, and 1/3. So A times each of those terms. And then C times our 1 and Z leaves us with just C. So we put together the vector. We start at the origin and we go backward in A1. We go backward, meaning away from the origin. So I'm going to go through that again. We're going to go backward to P, and then we're going to go -2/3 in A2, and then plus A/3. So 1/3 of A in the A3 direction. So we got to pay attention to our A1, A2, and A3 and whether or not it's negative or positive, and then how many thirds, because these are divided up into third steps. How many thirds are we going? So we start at the origin, we step back, we step -1 in A1, -2 in A2, and -1 or +1 rather in A3, and then we go up C, which is 3/3 in Z, and that's how we get to our point S up here. And that is how we get our unit vector for the crystallographic direction. 1 bar, 2 bar, 1, 3. So that may seem sort of like voodoo, but walking through it step by step, it actually makes a degree of sense. Determining the directions is the reverse order of the same process. So we're paying attention to what's happening with the A1, the A2, and the A3. So we figure out where the tail is and the head, and the tail coordinates are subtracted from the head coordinates so that we get these coordinates that we can normalize by the unit cell dimensions. So it's step by step undoing the same process that we just did. We adjust to the smallest integer values and then put it back into brackets with no commas for the 3-axis coordinates. And we can convert to the Miller-Bravais lattice coordinates using the formula below. So we're going to walk through an example of what this looks like. U, V, T, and W. It's helpful to know what each of these stands for. And these are equations that, for instance, we will give you on a test, but we expect that you will understand how to put them to use. So that's kind of the key there. So converting to 4-axis Miller-Bravais lattice coordinates. We'll look at an example of what that does, and then we adjust to the smallest integer values and enclose it in brackets. So what's all that gibberish mean exactly? So we start with a vector. So in this case, we've got an A1, an A2, and a Z. So in this case, we don't have an A3 component. We just have A1 and A2. We're just focusing on those two. So the tail location is at 0, 0, 0. The head location is at A, and 0, C. So we normalize by dividing by A or C as appropriate, meaning A over A equals 1, A over A equals 1, 0C divided by C equals 0. So that's how we get to our normalized values. The reduction is 1, 1, 0. The brackets are 1, 1, 0. Converting to 4-axis parameters, we take that and plug it into the formulas. So we calculate U to be 1/3, we calculate V to be 1/3, we calculate T to be -2/3, and W to be 0. So again, in this case, we're not making use of that that last direction. So this gives us our conversion back. So we multiply by 3 all the way across. That gives us our 1, 1, minus 2, 0. And to correctly notate that, we have our 1, 1, 2 bars, 0 in brackets. So that's how to do that in both circumstances. So both the forward direction and the reverse direction, to understand what the directions are. So with a few practice examples, this will make a lot of sense because it's fairly straightforward to follow. But let's take another look at planes now, which are different from the crystallographic coordinates and the coordinate vectors. These are crystallographic planes. So these are how are the crystal planes oriented relative to the unit cell. So a 001 plane is at the origin, but you can also have other examples of 001 planes anywhere throughout the z-axis, as seen in figure A on the left here. We also have 110 planes. So 1 in X, 1 in Y, 0 in Z, meaning that they are crossing, they are sort of infinite in the Z direction. That's what the 0 indicates. In the first case for A, 0 in the X and Y means it's infinite on the XY plane, and it is 1 in the Z. So it gives a reference point. 111 plane is triangular, and if you think about it, the way that safety glass, for instance, breaks. So when your car windshield breaks or a car window breaks, they typically make small squares. That's because they are more like a 110 plane, because that is a safer way for the glass to fracture. The 111 plane of simple float plane glass or float plate glass fractures typically along 111 parameters, leaving sharp triangular shards. And it is because of the crystallographic planes that it does that. So same material, it's both silicon dioxide, it's chemically identical, but practically in terms of their processing, they are very different. So 111 is a very natural state for the material. The reason that this glass is more expensive, among other things, is that it is a controlled crystallographic plane, so its conditions are more complex in terms of processing than simple float plate glass, which is a lot less expensive to make. So the reason why we put this in picture frames is so that when they break, they can stab us and we can bleed all over the pictures. The reason we do this in cars is so that we don't have to bleed when we get hit with the glass and it doesn't come through as sharp shards. They didn't do that originally, and they figured out, oh, gee, we should probably do something about that since we have the technology to do so. So it's important to understand what Miller indices. The reciprocals of the 3 axial intercepts for a plane, cleared of fractions and multiples, and all parallel planes have the same Miller indices. So we saw that the graphical representations of those. But the way that that looks is you read off the intercepts of the plane with axes in terms of A, B, and C, and then you take the reciprocals of those intercepts and reduce those to the smallest integer values, and then you enclose them in parentheses with no commas. So what that looks like in practice is this. So you find the intercepts, 1, 1, 0. or infinity in this case, and we'll see why that's 0. You take the reciprocals, 1 over 1, 1 over 1, 1 over infinity is 1, 1, 0. That's the reduction, because we don't have any other multiples in there, no other fractions. So the Miller indices are 1, 1, 0 for this example. So another example here is given. So our A, B, and C, we have infinite along B and C, but we have half of A as our intercept. So the reciprocal 1 over 1/2, 1 over infinity, 1 over infinity gives us 2, 0, 0. So the reduction of that, we don't need to further reduce any common multiples or anything of that sort, but this is the step where we would do that. Leaves us with 2, 0, 0. The only multiple we have in there is 2, so the reduction there we can do is divide everything by 2, leaving us with 1, 0, 0. Triangular example here. We can represent this with C being a little bit of a different fraction. So half, 1, and 3/4 might be our intercepts for the crystallographic planes. Then we have 1 divided by 1/2, 1 over 1, 1 over 3/4. So we get 2, 1, and 4/3. Then we multiply to get rid of the fractions. So our least common multiple there is 3. And so we get 6, 3, 4 as our reduction. And therefore Miller indices are 6, 3, 4 for that particular crystallographic plane. So it's not always single digit. There's not always a 0 or a 1. They can be just about anything. But those crystallographic planes, there are families of planes, and that's indicated by these curly braces. So the 1, 0, 0 family is fully represented by 1, 0, 0, 0, 1, 0, 0, 0, 1, 1 bar 0, 0, 0, 1 bar 0, and 0, 0, 1 bar. Each of those is in the same family because they are crystallographically similar to each other. There are some other examples of crystallographic families of planes that I think there's a list. I think there might be a list in the appendix or something like that. They also show that they have the visualizer that can help kind of make things easier to see, and it'll help to visualize some of these in the actual problems, because this is a kind of math and thinking that you guys haven't really had to do yet. So doing more test problems and example problems of this can be pretty tricky overall. So I know we're out of time here. So any questions as we go to close out? The bar is representing the negative value. So those are things that we will talk a little bit more about, because we'll have to do a couple more things here this next week to fill out some more concepts in detail for chapter 3 and walk through some more examples. So any other questions? All right. Well, I will work to slowly start getting you guys caught up to some semblance of normalcy. And if there aren't any other questions, then I will see you guys next week.
Professor?
Yeah. Questions?
Yeah, I did have a question. I don't know if you saw it, but I asked, what is the W again? Because you had W equals 0, but I kind of got confused on where you got that.
W is the fourth parameter of the W is the fourth parameter. We're going to cover some more of this in more detail this next week.
Okay, okay. And then will you be able to upload the recording today?
Yeah, I'm going to get it processing and then I'll be able to get it uploaded today.
Okay, yeah, because I I'm gonna want to review it.